A very good evening, everyone. Thank you very much for coming to the talk. Before I start to talk about some of the details, I want to do a very brief survey. How many of you have seen a self-driving car in real life? Oh, this is Silicon Valley. Great. How many of you have actually sat in a self-driving car? A lot less. How many of you are actually working in the self-driving car space? You know, anything related to self-driving cars, AI, computer vision, machine learning? Okay, a few. All right, great. So let's get started. So recently, the self-driving space has attracted a lot of attention. Mainly in the self-driving vehicles, such as self-driving cars, self-driving trucks, and self-driving robots. So for self-driving cars, there are a lot of companies, including the big companies like Google, Uber, Baidu, and also Apple, and also some of the traditional car manufacturers like GM, Ford, together with some startups like Zoox, Drive.ai, etc. They are all working on self-driving cars, mainly focused on transporting people around. At the same time, there's also another huge opportunity to move things around autonomously. Let's say for the long haul, in terms of the self-driving trucks, and for the last mile delivery in terms of self-driving robots. Let's dive into some of the details here. First, I want to talk about some of the brief history of self-driving car, and later I will talk about the self-driving robots and some of the latest statuses in our company. The recent development of self-driving cars would trace back to the DARPA Grand Challenge back in 2004. For the first challenge, the cars are supposed to travel for about 150 miles in the desert. And unfortunately, none of the team actually completed the whole course successfully for the first one. The only team that completed the longest course is actually from CMU. They completed about 11 miles out of 150 miles. Then DARPA decided to have another challenge, the second year, in 2005. This time, a lot more teams participated, and 5 teams actually completed the whole course. And the winner was the Stanley vehicle, this one, from Stanford, with a bunch of sensors there. The team was led by Sebastian Thrall. And then the second place actually went to CMU. Then in 2007, they thought, probably the desert environment is not challenging enough. So they decided to move this to the urban environment. So they called it DARPA Urban Challenge. This time, the CMU team actually won the first place, and the Stanford team won the second place. So they traveled much faster than those in 2005, and 7 teams completed the whole course. And later, Google saw the big opportunity there. They, went to Sebastian Thrall and invited him to join Google to develop the self-driving car technologies. And so they basically started the project in 2009, and this is one of the vehicles in 2011. And then, so at that time, the car was actually modified, with a bunch of sensors integrated, but it's still relatively separate. Then in 2014, they actually made a new model that is very different from the previous model. There's no steering wheel, there's no pedal, and yeah, so this time, and also the autonomy level is also a lot more than the previous one. So by far, the self-driving cars at Google have traveled more than 3 million miles autonomously, all by itself, not including the simulation miles. Then, a lot of other companies also started to dive into this space. So why are so many companies interested in this space? There are at least 3 reasons. First of all, it can reduce the traffic death. Every year in the world, there are about 1.2 million people dead, because of traffic, and that is about 42,000 in the U.S. alone every year. Sorry. So with self-driving cars, it can actually reduce the number of deaths significantly because a car can drive better than an average human. And also, it can also save time. There might be a lot of traffic jam. I believe many of you have experienced this. And with a self-driving car, you can do whatever you want in the car. And also, it can help the elderly and disabled to travel around more freely and independently. So there are different classifications of the autonomy levels. One of them classifies them into 6 levels, from level 0 to level 5. Level 0, basically, there's no autonomy at all. And level 5 represents full autonomy. And so currently, many of the companies actually lie somewhere from 2 to 4. Level 2 is more like the autopilot, for example. So how does this all work? Why a car can drive by itself? What's the magic behind it? So this is an overview of a typical self-driving system. It includes the hardware, the sensor part, the actuator, etc. And on the right side is the software. The hardware and software basically are interacting with each other seamlessly. The sensors can help sense the environment for the car to do the perception and also to localize itself. Then it can do the planning based on the perception, and it sends the driving command to the actuators to actually move towards the destination. There are many sensors for the perception aspect. These are some of the popular ones. The reason to have so many sensors is mainly because a single sensor can only be good at one single thing, or at most a couple of things. Sometimes you want to do cross-checking, and sometimes you want to utilize the different advantages of different sensors. For example, for GPS, which is readily available nowadays, the accuracy is not good enough for self-driving cars. Normally, the accuracy is within meters. If you rely on GPS alone, even if the car is driving into the next lane, you're not going to know that. So fortunately, we have other sensors to sense the environment and localize the robot or the car. So LiDAR is one of the popular sensors. It can give highly accurate 3D mapping data. It can be 360 degrees, and it normally sits on top of the car, like this one. but it has no color information, and it is also relatively low resolution compared to cameras, say. And it is very expensive, very expensive. For, let's say, the 64 channel LiDAR Google is using, it costs over 70,000 US dollars for that device alone. So it's pretty expensive. Even if you use, let's say, 16 channel LiDAR, that's still $8,000. But it can be very reliable. So for self-driving cars, a lot of the companies still use LiDAR, expensive one. Also camera is also a very popular sensor. It has a high resolution with color information. It can be good for classification and detection. It's not expensive at all. Normally, a couple $100 can give you a pretty good camera. However, it's sensitive to lighting conditions. For example, shadows or night driving camera is not so good. Another type of sensor is the radar. It can measure the motion of the car pretty well, but it has low resolution. And there are some other sensors as well, in addition to GPS. For example, ultrasonic sensor, more for close-range obstacle detection, and IMU more for for sensor fusion to get a better estimate of the odometry. So, in terms of perception, environment perception is a very important step. It basically, the car needs to know what's around it, what kind of obstacles it is seeing, and how are they moving. And also, it needs to know what the traffic light is, and also read the road signs in order to follow the rules of the road. For obstacle detection, it includes the pedestrian detection, vehicle detection, such as cars, bicycles, motorcycles, etc. In this image here, you can see from the camera, you can see the different types of the vehicles and pedestrians, and they are also indicated in the map. So this is basically showing some of the LiDAR points obtained from the better than 64 channel. When you collect a bunch of those images or 3D data, using deep learning, you can get a good estimate of other objects at the same time. So deep learning using convolutional neural network is a very popular approach. Actually, one of the dominant approaches for obstacle detection, various obstacle detection. Another important aspect is for the car to know where it is within the real world. In order to do that, it needs to build a map first. This map is different from the Google map we are typically using because the robot needs more accurate maps, even HD maps. And after it has the map, it uses the map to do the localization. The localization basically solves the problem, where am I in the world? This world means the map here. And in order to do the localization well, typically people use different sensors and fuse them together. Use common filter, for example, to get a better estimate of where it is. There's a third category which is also very popular called SLAM, simultaneous localization and map. As the name indicates, it basically tries to build a map and localize it itself at the same time. It solves the problem of where am I in this unknown world. So on the right, it shows visual slam image. On the top, it's some images from a video, from a camera in front of the car. And at the bottom, it's building the map and localize itself at the same time in the map. So you can see the map is actually growing. This is called visual slam. So we talk about mapping and localization, environmental perception, etc. So there's also another very popular category of doing the self-driving technologies. It's called end-to-end deep learning or self-driving. NVIDIA published a paper on the end-to-end deep learning using a single camera. And they basically take the camera images and correspond that to the steering command. They collected 72 hours of training data, basically driving data, and trained it using a convolutional neural network using this structure. And after training the model, they again use that to predict the angle from the images from a single camera. For example, this is an image the car actually sees, and these are some of the high-level features that it predicts. And based on those, again, it outputs a steering command, like turning left or right by how much. That concept itself sounds pretty simple, but it worked really well. So this is one of the examples of the self-driving using actually the end-to-end deep learning approach. You can see the hand there on the top. And they actually showed it not only works in normal environment, but also in different scenarios. Let's say on the highway, on the curvy road, like this one, and also even in different weathers, like rain or snow. Pretty amazing, huh? So they actually achieved 98% of autonomy level, 98%, using the data, amount of data they collected. So some people may be wondering, which approach shall we use for self-driving car technologies? Shall we build a map first and localize it? Or shall we just use the end-to-end deep learning and skip all the steps? Skip perception, skip planning, skip cannot skip the control part. But so which approach shall we use? So actually it turns out that there are different merits, advantages and disadvantages for different approaches. For example, for the self-driving, for the end-to-end deep learning, it works up to the standard of 98%. But is that good enough? No, not at all for self-driving cars. What does 98% mean? That means every 100 miles, you need to take care of the car for 2 miles. But it's 2 miles, but you have to take care of that for the full time because it's not fully autonomous. So that shows some promises, but it's not good enough for self-driving cars. For self-driving car, because it's very mission critical, normally there's a person or even more people sitting in the car. You want to make sure the car is 99.99, many 9% autonomous and safe. So, and that's also why so many companies are working on self-driving cars, but it's very difficult to get it actually on the road for real commercial use. It's basically some of the corner cases are normally very dangerous. You might see some of the cases, some of the news reports about the crashes in self-driving car, etc. That's also why a lot of companies are taking very cautious steps about really putting it on the road for the real world use instead of pilots. So then what could be a good approach? So also for deep learning, it's like a black box in many ways. It just takes the input, you train it, you don't know what's happening inside. So if you want to make it better, if you want to make it like 99.99% from 98%, that's very difficult just by using deep learning alone. But if you can combine those two different approaches together, let's say math-based or rule-based, together with deep learning, if you can see, let's say, if you can use deep learning as some of the intermediate steps instead of final steps, you can actually eliminate some of the corner cases. So that's more like a combination of the two approaches. Let's say even in the math-based approaches, they still use deep learning in obstacle detection, and they do the cross-checking using multiple sensors, etc., to make sure the corner cases are actually successfully captured. All right, so that's all about self-driving cars.
What is CNN stand for?
Convolutional neural network. It's a very popular deep learning neural network architecture. Yeah. So the self-driving cars are mostly to transport people around. Let's say robotaxi, like what Zoox is doing. There's another type, self-driving robots for last mile delivery. So McKinsey has a report about the last mile delivery models in the future. So currently, the last mile delivery is mainly by humans, and in the future, there may be another few types using self-driving robots, cars, and even drones. And actually, they are already happening today. Among these, I'm going to talk more about the self-driving robots. So let's first take a look at the whole market in the US. Every year, there are about 12 billion deliveries. This is number of deliveries, not the actual dollars, for food and packages alone, not even considering the grocery delivery part. And this is also only in the US. In China, there are about 31 billion packages, only packages delivered every year. That's a huge number. And also, this number is actually growing every year. In China, it's growing at 30%. So, in terms of the cost, currently in the US, for food delivery, let's say, for example, it costs about $5 to $10 per delivery. Let's say if the food value is about $10 to $15, you need to pay extra, probably $7 to $8 using the current approaches. And that's very expensive. That's a high percentage of the food value. Using robots, however, it can drive the price down to $1 to $2 only. What does that mean? If you are eating in a restaurant, you're still going to pay the 15% tips. So this $1 to $2, this is about the same as the tips. So imagine in the future, with self-driving robots, if you get a food delivered to your house, it's going to have very similar price as if you are eating in a restaurant. And one of the customers said, if the cost of food delivery drops to $1, I will order that every day. Actually, this is a very typical reaction. We did a survey back in Boston. So currently, about 30% of the people order food delivery at least once a week. If we drop the price down to $1 to $2, that percentage is going to increase to 77%. That's more than double. So, here comes the Robbie the robot. At Robbie Technology, we are building the self-driving robots for last mile delivery of food, grocery, and packages. And they travel on the sidewalks. They can reduce the delivery cost significantly. When the cost is reduced, the market will also further expand. And this is a picture of the version we currently have, which was made a few months ago. And here's our team. I had a PhD in computer vision and robotics at MIT and graduated in 2015. And Ira, my co-founder there, at the back. Yeah, he had his undergrad, master, and PhD all from MIT. He was doing LiDAR and robotics. So computer vision and LiDAR are in the center of self-driving technologies. And we also have an awesome team of engineers. Carl is doing mechanical, he was from Boston Dynamics. And Vinay is also here today. Yeah. We also have a system integration engineer, industrial designer. Hongju, also stand. So basically, a team from Robbie Technology stand up so that after the talk, people can talk to you. Yeah, can you stand up? Okay, great. So an overview of Robbie Technologies. We basically started the project in March last year, and we got accepted to Y Combinator last summer, and that's when we moved here, the Bay Area from Boston. Then we tested the food delivery at Stanford in July, and started the pilot program with a major delivery company since September. And we have the cases professionally manufactured last December. And started the pilot program with another major delivery company. Okay, here is some of the iterations, versions. This was the first version was built in June. Actually, we built it from scratch after we moved here in 2 to 3 weeks, and we quickly iterated on that. This is also manually built in our garage in August. Then we have a professional manufactured phase in December. So let me show how our robots look like in action. In this video, everything is fully autonomous. So basically, when the robot drives to the destination, the user unlocks the robot by pressing a button on the phone, and then takes the stuff out, and it locks it and goes to another destination. At the same time, the user is able to see the robot on the map, no longer. So it basically shows the robustness of the robot. Even after, this is showing it stops in front of people, even at a very close distance. And I was trying to mess around with the robot. It's pretty sensitive. And also, if something is blocking its way, it also stops and goes again. So if it detects that it's a person other than some other obstacle, it will actually say something like, "Excuse me." And yeah, this is basically showing the going curvy road. So let's say after the stop in front of the person, after it said "excuse me," if the person moves away, it will actually say "thank you." So we try to make the robot as social as possible. And if the robot, basically the robot can detect the different types of obstacles, not only pedestrians, also cars, even dogs, cats, etc. So that, and also bicycles, of course, so that it can take different actions based on the detection results. So these are some of the pictures for the pilot deliveries in the Bay Area. Like we started the delivery in Stanford, with the very first rough version, and it got interested by a lot of people. And we actually delivered we delivered the lunches and milk tea last summer at Stanford, and it was very well received, and a lot of people kept asking me after that when we are going back again. And the answer is pretty soon. And this is some of the pilot delivery with one of our partners, one of the delivery companies. And this is also with another delivery company. So for all the things we do, we always put safety first, because that's the first priority in all types of self-driving vehicles, and they should value people's lives. And so in this case, it can detect very different types of vehicles and pedestrians and stop in front of that. Like this guy is trying to mess around with the robot. It actually after it stopped. By making different actions there, and this is very typical. Some kids, they're very playful. They're trying to play with the robot. And we actually also have two-way communication. So if the robot stops in front of some obstacle for too long a time, we will know that, and we can take over. So yeah, this is detecting a car at the driveway, and this is detecting the bicycle. So you might be wondering, there are many different types of vehicles for last mile deliveries. So what are the different advantages and disadvantages? Let's say one question we were asked is how is it compared to self-driving cars for last mile delivery? For a number of reasons, actually, self-driving robots are more advantageous. For example, the self-driving robots, they run on the sidewalks, they travel at a slower speed, and they can stop at any time if the robot is uncertain about something. But for a car, that's extremely difficult and dangerous. Imagine if a lot of cars are stopping in the middle of the road, that can create a lot of problems. So that's also why the self-driving car companies are trying to make their car like pretty much fully autonomous. before they can really go onto the road. For the robots, when the robot stops on the sidewalk, you can actually ask for human assistance, tele assistance. So we basically can monitor what the robot sees at every single second, and we know when the robot is in corner cases, we can help the robot remotely, basically. We also have two-way communication. So it's basically also like a phone. We can talk through the robot to the pedestrians or other situations. So in that sense, it is also remotely controllable in those corner cases. And that's one of the key differences between self-driving robots and self-driving cars. So that we can actually deploy the robots as soon as today, not in 5 years or 10 years. And so the technology is actually ready for deployment. So the amount of autonomy level, let's say, when the autonomy level for robots is 0%, that means the remote control needs to be 100%. And a person needs to monitor and control the robots all the time. When the autonomy level is at 90%, that means one person, only 10% of the time, the robot needs human assistance. So that means one person on average can take care of 10 robots. If the autonomy level is 99%, that means one person, only 1% of the time, the robot needs taken care of. So that one person can actually take care of 100 robots, let's say. So for the in that sense, the technologies are actually ready for deployment. And also it is safer because the number of situations that robots encounter are much fewer than that on the road, and low cost. And also interestingly, we find that it is also a great advantage in the, let's say, downtown area. When the delivery is, let's say, within a few blocks or a mile, let's say, it's often hard to find a parking space, in the downtown area. But for a robot, it doesn't need to find a parking space. In that sense, it can actually go faster than a car. In terms of the, let's say, overall time. So there's another types of delivering vehicle, the drones. There are a few companies working on the drone deliveries. In our opinions, drones are still not mature yet for a number of reasons. The drone battery normally only lasts, let's say, minutes. Let's say 20 minutes to maybe maximum 1 hour. Also, the weight it can carry is pretty limited. If you need to carry a 10-pound stuff, the drone needs to be very powerful and possibly very large, which can be dangerous in the urban area. So, and also the legislation for drones, the legal aspect is a big hurdle nowadays. So some states have passed the law to allow drones to fly in the sky, but you need to monitor that. You need to keep an eye on keep the drones in the sight of a human. That means it's pretty difficult for it to go autonomously. You cannot, just run with the drone on the ground, right? So in terms of the legislation processes for self-driving robots, currently there are a few cities and states that actually already approved this type of robots to go on the sidewalks. That includes the Washington, D.C., Redwood City, and also 4 states, Virginia, Idaho, Wisconsin, and Florida, more recently. And there are also a lot of other states and cities being talked with. So, driving into the future. Imagine 10 years from now, when you press a button, when you order something on your phone by pressing a button, a robot in, let's say, Whole Foods, they pick up the items and send it to another robot to deliver it to right in front of your doors at very minimal cost. How will that be like? It's actually starting to happen, and it's happening now. Recently, like Amazon, is probably going to acquire Whole Foods. One of the imaginations people think of is actually combine Amazon Go with Whole Foods, and what would be the natural next step, or probably this step, to do the deliveries autonomously. And also in the Amazon of China, Jingdong, the second largest e-commerce companies in China, they actually announced some pilot delivery using self-driving robots right last month in several campuses in China. So that's the future, and that's also now. It's actually happening today. So we are RobotX Technologies. We are building self-driving robots for last mile delivery. And we believe that can be a big game changer for local deliveries, and that can help boost some of the local businesses as well. We are thrived to build that future from today. If you're interested in building the future together, we are actually actively hiring. Check out our website, and I will be. That's all for my talk today. I'll be very delighted to answer any questions.
Okay, great. So the first, thank you. Yeah, great. So I have the first question. Answer will asking represent the RobotX team. Sorry.
Yeah, Roy, can you talk more about the self-driving robots? Will be the market in China, the potential in China?
Sure. So in China, let me give you some numbers first. The number of packages delivered every year in China is 31 billion. On this, in China we have the Singles Day on November 11th. They call it 双十一 Double 11. On that single day in 2015, the number of packages delivered were actually 680 million on a single day. So, and that number is actually growing at 30% every year. You can imagine, the number of packages that need delivered is growing, and also at the same time, the labor cost is actually also growing. So there's a big contrast there. I can imagine in the future, many of the deliveries will actually be done autonomously. Let's say, McKinsey have a report that says 80% of the deliveries in 10 years will actually be done using some kind of autonomous vehicles, including robots, cars, or drones. So, and in China, it's definitely a big growing market.
Thank you. Who's next?
Yeah, so you talked about the regulatory, you said 6 or 7 cities and states were approved. So can you give us a thumbnail sketch of what the main regulatory issues are preventing wider wider approvals? I mean, so what is the big, I mean, with self-driving cars, we know what the issues are. Can you give us a thumbnail sketch of what the main issues preventing more cities and states coming on board?
Yeah. So so actually the approval process started from only last year.
Okay.
So from last June, it's about a year, and those cities. So for many of the cities or states, they actually have existing regulations, that haven't taken into consideration this type of new vehicles on sidewalks. So they simply, people probably haven't imagined there's such type of robots going on the sidewalks one day. So that's one big aspect. So it takes time to communicate with those cities or states to get them to know that this type of robots can be very beneficial to the community, can be they are very safe, etc. And at the same time, some of the cities. So currently there's actually no law. Interesting, there's no law banning this type of robots. It's more like about getting formal approval to do this type of testing in order to, let's say, not disturb the local residents, etc. So it's basically the process takes some time, like self-driving cars. They start from some states, and then more and more states we start to accept that. That basically takes time.
But is it the case that the cities want to extract some revenue from this because you're using city resources? Sidewalks, cars are taxed to maintain the highways. So similarly, is it that issue, or is it more of a certification issue, or what is it, in your opinion?
In my opinion, I think it's well, the cities, let's say, at the city manager level, or probably they want to, whenever they approve some kind of new laws or MOUs, they want to make sure it's actually working well, it's safe, it's beneficial. So they need some data, some stats, because this is a very new type of vehicles. So so they basically they of course also want to boost the local businesses by approving this.
Thank you.
So what kind of technology uses NVIDIA, camera, how it goes? And how much is the cost on each robot?
Okay. So in terms of the type of the sensors we are using, I cannot talk too much about the detail, but on a high level, as you can also see from the video here. So for this video, we are mainly using cameras and sonar sensor, ultrasonic sensor. Here, so this is the back of the robot. Basically, there are cameras on every side of the robot, and more cameras on the front side. Basically, we use computer vision and machine learning, and to do all kinds of tasks. So the reason so comparing cameras and LiDARs, cameras are relatively low cost. At low speed, it can work pretty well in the day, and in let's say in a variety of situations, like NVIDIA showed with a single camera, even on a car, even at a relatively fast speed, it can work relatively well. For robots, let's say since slower, the speed is even slower than a car, it's also working very well. But at the same time, you also need to do many different types of detections, detect different types of obstacles. Yeah, so there are, cameras can be very useful for mapping, localization, or deep learning, etc. But they are not working so well at night. So.
Yeah, one question is, let's say if your robot is going, something is coming very fast, sound mechanism to hear the sound is coming faster than your speed and they collide each other?
So let's say, you mean from the front?
From the side.
From the side?
Yeah, let's say from the doorstep.
Oh, you mean for the driveway?
Yeah, driveway.
Okay, let's say for the driveway.
Yeah.
The robot is running on the sidewalk and there's a car.
Yeah.
So there are different situations here. If the car is already stopped on the driveway, the robot will actually stop, at a distance because it can detect that pretty well. And if the robot is already on the driveway while a car is driving, from a distance, the robot can also see the car, let's say from the side cameras, and it can also take some precautions. So at that time, it's actually, so the robot is already on the sidewalk. It actually has the right of the sidewalk, right of way. Yeah.
Yeah, for that question. So last mile, you can also cross the road. For example, right now, even in 1 mile ago, you may have to pass the road. So the side road is not connected. It may be disconnected.
Yeah.
So can this robot cross a road?
Yeah. So sidewalk. So it depends on the situations. Let's say for crossing the road, normally because there are cars and running around, and it might be a little bit more mission critical. So initially, for our approach, whenever the robot needs to cross the road, we take care of that manually. But on the sidewalk, which is the vast majority of the time, we can go highly autonomously.
So that means for any post or delivery, you need a human involvement.
So that's related to that's our initial step, because the crossing the road is actually a long tail effect. Like, for example, for self-driving cars, the last 1% or even 0.01%, that needs a lot more resources than the first 99%. Let's say, many companies can develop a self-driving car that can run, 99% or even 99.9%. But it's extremely hard to get it to 100%, or let's say, 99.999%. That's extremely difficult. So our approach, we basically, so for the crossing the road, which is more mission critical, we are dealing with it over time. That's not our first priority for now, but we are dealing with it over time.
And I ask another question. And how long the battery will support? Let's say how far this robot can go?
It can go for majority of the day. Yeah.
Thank you.
Hey, so my question is, can I kidnap this robot? So I see it on the road. It's super cute and it's a lightweight, and I want to take it home.
Good question. Over 95% of people we talk to ask this question. So we have different measures. It didn't show in the video, but actually when you push away the robot, okay, so first of all, the robot is always locked. Only the end users can open it, can unlock it on their phone. Also the robot, if you push the robot or touch the robot while it's running, it will actually sound an alarm. And also it will, because it detects something unusual, it's not from itself, it's from the outside forces. It will also start the camera recording because it's unusual situations, and also it has the GPS tracking. So pretty much, it's very difficult to kidnap such a robot without being captured.
For the autonomous mode, are you going towards robots end-to-end driving way or using the map way? Like
Sorry.
so for the autonomous mode, you discussed two modes, right? One is end-to-end learning, like it NVIDIA did. The other one is using the map.
For self-driving vehicles.
Slam.
SLAM.
You mean SLAM?
So which way are you going? Or which way do you think is better?
That's a secret.
What kind of wireless technology are you using for telematics?
Wireless
Technology for telematics, cell, or
we're using 4G.
4G?
Yeah, well, yeah.
Could you talk about what kind of efficiencies you're bringing in, percentage efficiency or cost efficiency you're bringing in, given that this can, I'm assuming this can deliver one package at a time compared to a drive-by which can do a few more. So does this come back to the homing station per second delivery?
So for this version I'm showing here, so this version it has a single compartment. So our next version we will have multiple compartments so that it can host multiple items. So when the robot is delivering, it can actually basically pretty much similar to what let's say Uber does. Basically, the robot can stop there at the destination and waiting for the further order, and takes the order nearby basically and deliver to the neighborhood. And at the end of the day, it will go back to the station.
Where is the station located? Where does it get launched from?
The stations will be nearby, every, let's say, few miles. It can be some a simple space, rented for storage. It's not very special.
So what's the speed that you're operating?
Speed, so for the one showing the video is called walking speed. In actual fact, it can go much faster. So basically, we are running between walking and running speed. When there are no people around or in the front, it will run faster.
So did you have any problem with the legislation in that case? Because there are sidewalks or places where bicycles are not allowed, only people can walk. So
yeah, we can mark that. So then, if the robot first encounters that, it will note that down, and in the future, other robots can avoid that area, when doing the routing.
Can you use bike lanes?
Bike lanes, currently, if the bike lane, there are two types of bike lanes. One type is on the road, the other type is also served as a sidewalk. So we only operating on the sidewalks. Because once you get onto the road, you basically have the same problem as self-driving cars.
Do you have an estimate of what
the cost to deliver is using when your robot is fully functional?
So after the robot is built, basically the cost of delivery is pretty much the electricity and the maintenance.
Depreciation.
Depreciation. Yeah. So in that sense, it's very little. So the huge cost is actually the hardware cost.
I mean, today JD is at $1 already for delivery.
You mean JD.com? Yeah. So JD.com, they are doing pilot deliveries in some campuses in China. Yes. Yeah. It's basically pilot deliveries.
I mean, does that say it's less than $1 per delivery per human?
I'm not sure the price of direct delivery. So initially it can be high.
Yeah.
Is JD using your robots?
JD, they are developing their own robots.
And who is using your robots today?
we have some partners, some major delivery companies, which I cannot say the names yet. We're going to have some news soon.
Sorry. How does Robbie compare to like other self-driving robots that are like about to be on the market or potentially? Like I think DoorDash is developing their own robots as well.
Great question. I have a slide for that actually. So these are some of the companies building delivery robots like Starship, Marvel, Dispatch, and Domino's. This is Jingle, and this is by Segway. And there are also other delivery robots out there as well. So comparing with them, our advantages are mainly in three aspects. So first of all, we are in terms of the technologies. So we have the right expertise in this field, in the self-driving space. We basically, although we only have a number of people in our team, we actually we basically built the robots since last year, and it's already operational. We did highly autonomous, did pilots with some major delivery companies, and so we move very fast, and that's also because we have the right expertise. We are definitely not the first company to do this. We actually came up with the idea independently, like earlier last year, but we are already ahead of many of our competitors. The third aspect advantage for us is actually we are not using expensive LiDAR. Like as you can see the LiDAR here, this is the 16-channel Velodyne, which costs $8,000. Our whole robot is a lot cheaper than that. So they're also using LiDAR. So basically, right expertise, we move fast, and our cost is low.
Is delivery the only area you're looking at, or is there other applications?
So currently we are like mainly focused on the last mile deliveries.
Anything?
Like food packages, groceries.
So without LiDAR, you guys cannot deliver at night. Because basically the camera with LiDAR they can deliver at night, so they use it most of the time.
Good question. And I said we are not using expensive LiDAR. We are using some cheap LiDAR combined with other sensors. It's not shown in the video. We are actually working on that. So it will be able to work in the night pretty soon.
How far do you expect each of the deliveries to be from each source?
Sorry?
How far do you expect the deliveries for each?
For each delivery.
Yeah.
So it's mainly the last mile is actually a term to mean the local deliveries within a couple of miles. Let's say we are targeting at let's say within 2 to 3 miles. So that's actually where a majority of the deliveries happen. Local deliveries happen. Food for food, groceries, and, also for packages. Every package has to go to the last mile delivery, which is interestingly for the package delivery, the cost of the last mile delivery is actually about 30% of the overall delivery cost. So that's a huge amount.
So does it walk on grass and other types of roads? And how do you deal with the roads that are in San Francisco, like those up and down hills?
Yeah. So going down and up, that's not really an issue. It can also go on different sidewalks. Let's say we tested it in some downtowns. It can work pretty well. In terms of grass, currently we intentionally do not let the robots to go on the grass for a number of reasons. For example, let's say in the Bay Area, there's a lot of grass on the two sides of the sidewalk. And if you let the robot go on the grass, for some parts of the grasses, there might be something else. For the it might be hard for the robot to get out. Or people might try to force the robot to go on the ground, try to play with the robot, things like that. But when needed, we can also adjust that. But normally we don't allow you to go on certain terrains. But mechanically speaking, our next version, which will come out soon, we'll be able to deal with many different types of terrains, including different slopes that are even very steep, like curves and grass, sands, even water or some bumps, etc.
So some of the really steep streets in San Francisco have steps on the sidewalk.
Yeah.
So that's not accessible.
Yeah. So steps. For current version, the one I'm showing here it's not intended to go on the steps. But our next version, you can. Yeah.
How many miles have your robots driven, and what percentage has been autonomous?
Good question, and some part is confidential. So we have been testing it since last year, and we didn't have the exact number for the number of miles, but it's definitely many hundred miles without a single accident. And the autonomy level from the beginning to now currently is highly autonomous. Very high. I cannot say the exact number.
Great. How many questions you want to keep asking? That's the two?
Maybe two others. Yeah.
Two others. Okay, one from here and one the other from here. All right.
So how do you expect this market to develop? Do you expect that it'll be the urban areas that come first, or suburban areas where there's more space for these things to drive around? How do you see the structural development of the market?
Yeah. So the urban areas and suburban areas, they have different advantages. For the urban area, that's where a lot of the delivery happen. But at the same time, there might be more people going around. So the robots might be able to find some routes that have less pedestrians. In the suburban area, there are less deliveries. It's good for the robots to run faster, but it's normally a longer distance. So for us, we are doing that actually in both areas. We are testing that and see which one is better. Yeah. But eventually, no matter where to start, definitely in the urban areas, that's where a lot of the delivery happen. The robot needs to go there.
What are your biggest challenges? The business or technical?
Yeah. So biggest challenge is because this is a new type of vehicle. So the social robot interaction part can be, very interesting. That's also something we have been testing, and it also shows some promises. At the same time, so it's always interesting to see some new scenarios, like how people interact with this type of robots and how they can accept this type of robots in their society, let's say. So we're trying to make the robots as socially capable as possible.
Okay, great. Thank you, Ray, for great sharing. And the rest of our will is the network. Thank you.
Thank you very much.